Hello and welcome back to Calero Academy. Today we're going to be investigating a very neat probability and statistics trick. The trick asks us to prove, want to show that the probability of 3 heads in 6 tosses of a fair coin is equal to the probability of getting 3 heads in 5 tosses of the coin. Now, that would seem counterintuitive. How could that be? Because after all, it would seem that if you get an extra toss, surely it increases the sample space and somehow it would seem to help you. It would seem that it would give you more chances to get 3 heads. But it turns out that they are equal to each other and they're equal to 5/16. So, we could of course prove this by just drawing an event box. However, I want to actually use the binomial PDF to prove this, because after this I'm going to prove that this is actually not just true for 3 heads and 6 tosses and 5 tosses, but actually you can generalize this and scale up the heads. So that's going to be very interesting. So I'm going to break this video into 2 parts. In the first part I'm going to prove that this is true, and I'm going to show the generalization. And in the second part, I'm going to show some very interesting corollaries to what we've just proved in the first part. So, going ahead, proof. Let's remind ourselves of what the binomial PDF looks like. It is f of n, x, and p, where n is the amount of trials we're doing, x is the amount of successes we want to see in those trials, and p is the probability of getting a success in those trials. So, let's show that this guy is equal to 5/16, and so let's plug in. Therefore, 3 heads, x is equal to 3, n is equal to 6, and p is equal to 1 on 2. So we can write as the probability of 3 heads and 6 tosses is equal to 3 f of 6, 3, 1/2, which is equal to, this is the general PDF for the binomial function, n choose x times p to the power of x times 1 minus p to the power of n minus x. Plugging in, we will have that it's equal to 6 choose 3 times p 1/2 to the power of 3 times 1/2 to the power of 6 minus 3. Or simplifying, going to the next line, 6 choose 3 times p 1/2 to the power of 6. Okay, we're driving towards 5/16, so let's expand the 6 choose 3. This is going to be equal to 6 factorial on 3 factorial times 6 minus 3 factorial times 1 on 2 to the power of 6, which is equal to 6 times 5 times 4 divided by 3 factorial, because 3 factorial over here gets rid of the 3 times 2 in the 6 factorial. So this is times 1 on 2 to the power of 6. Simplifying further, this is going to be equal to 3 factorial is going to be 6. So 6 over here divided by 3 factorial is going to get rid of that. So we're going to be left with 5 times 4 on 2 to the power of 6, which will equal to 20 on 64, which will equal 5 on 16. Now let's show that we've done half of our proof now. Let's now show that the probability of 3 heads in 5 tosses is also equal to 5/16. So our binomial function says it's f of 5, 3, and 1/2, which is plugging in 5 choose 3 times 1/2 to the power of 5. Okay, expanding our 5 choose 3 is going to be 5 factorial on 3 factorial times 5 minus 3 factorial, which is 2 factorial, times 1 on 2 to the power of 5. 3 factorial gets rid of, in the 5 factorial, 3 times 2. So on the numerator, we'll be left with 5 times 4 on 2 factorial times 1 on 2 to the power of 5. But 2 times 2 to the power of 5 is simply 2 to the power of 6, so we'll be left with 20 on the numerator divided by 2 to the power of 6, which will be 5/16. So, therefore, writing our success box, we've proved that the probability of getting 3 heads in 6 tosses is equal to the probability of getting 3 heads in 5 tosses. Forgive me for the ugly success box. So, now let's try to generalize. It turns out that it actually, as you scale up the heads to 4 heads, it's actually going to be true that the probability of getting 4 heads in 8 tosses is equal to the probability of getting 4 heads in 7 tosses. So, to prove this generalization, we're going to have to perfectly articulate our want to show. If we notice the pattern, 3 heads, 6 tosses, 4 heads, 8 tosses, let's define the probability for the generalized one as want to show that the probability of getting n on 2 heads in n tosses, because that's really all it is equal to the probability of getting 3 heads in m tosses, where m is equal to n minus 1. n minus 1. m is equal to n minus 1. Where m is equal to n minus 1, we have to write in our want to show. And n is an even number, or in a fancy way, 0 mod 2. So, proceeding to the proof. Now, what we're going to do is we're going to go through a series of equivalent to show. Basically, we're going to evaluate these guys, each of them, and then we're going to say it's equivalent to show that they are equal to each other. Then we're going to keep on driving down until we have shown that it's equivalent to show that 2 is equal to 2, or something like that. That will make it extremely... That will mean that it is generically true. It's true for no matter what n is. N and m is. So, first let's do this guy. This guy is, in our binomial function, f of n on 2, and p, where p is still 1 on 2. That hasn't changed. Which will equal to n choose n on 2 times the probability, 1/2, to the power of n. I'll write the 1/2 in there later. So, that's an expansion of this guy. Now let's do this guy. That guy will be equal to f of n on 2 and 1/2, where p is equal to 1/2. Therefore, that will be equal to m choose n on 2 times p to the power of m. Now, let's substitute immediately m is equal to n minus 1 into there, and we'll get the probability of 3 heads in m tosses is n minus 1 choose n on 2 times 1/2 to the power of n minus 1. Okay. Therefore, it's equivalent to show, since all we've done is just expand these guys, this guy and this guy, it's equivalent to show that their expansions are equal to each other. So it's equivalent to show that n choose n on 2 times 1/2 to the power of n is equal to n minus 1 choose n on 2 is equal to, therefore it's equivalent to show that n choose n on 2 times 1 on 2 to the power of n is equal to n minus 1 choose n on 2 times 1 on 2 to the power of n minus 1. Okay, now let's just keep on going down. Let's just expand both sides. So therefore it's equivalent to show that n factorial on n on 2 factorial times n on 2 factorial times 1 on 2 to the power of n is equal to n minus 1 factorial on n on 2 factorial on n on 2 minus 1 factorial. If you're wondering how we got that term, it's because we have to write in the second part of the denominator n minus 1 minus n on 2 should just be equal to n on 2 minus 1. So this times 1 on 2 to the power of n minus 1. Okay, so now let's do some simplification. We can get rid of the n on 2 factorials. They're both equal to each other. It doesn't change what we want to show if we multiply both sides by n on 2 factorial. Next, let's multiply both sides by n on 2 minus 1 factorial. That will mean it's equivalent to show that, let's now write on 2 lines to give ourselves clearer space. It's n factorial on n on 2 times 1 on 2 to the power of n equals n minus 1 factorial divided by 1 times 1 on 2 to the power of n minus 1, because all we just did is multiply both sides by n on 2 minus 1 factorial, and that will get rid of everything behind, if you want to think of it that way, behind the factorial of n on 2. Therefore, it's equivalent to show that dividing both sides by n minus 1 factorial will get rid of everything behind n in n factorial. So that will leave us with equivalent to show that n on 2 times 1 on 2 to the power of n is equal to 1 on 2 to the power of n minus 1. Multiply both. Now let's just times this, multiply this side to over there, and we'll have its equivalent to show that n on n on n on 2 is just 2. It's equivalent to show that 2 times 1 on 2 to the power of n is equal to 1 on 2 to the power of n minus 1. But looky right here, if we would divide both sides by 1 on 2 to the power of n, we're going to have that it's equivalent to show, forgive me for that was a little bit below right then. So it's equivalent to show that 2 is equal to 1 on 2 to the power of n minus 1 divided by 1 on 2 to the power of n, which is equal to 1 on 2 to the power of n minus 1 minus n, which is equal to 1 on 2 to the power of minus 1, which, as everyone knows, is equal to 2. Therefore, it's equivalent to show, if we want to prove that the probability of n on 2 heads in n tosses is equal to the probability of 3 heads in m tosses. Forgive me over there, it's supposed to be n on 2 heads in m tosses. Sorry about that. Those things are equal. It's equivalent to show that 2 is equal to 2 if we want to prove that that is equal to that. And since 2 on 2 is always going to be equal to 2 is always going to be equal to 2, we've just proven the generalized formula for the trick, that the probability of n on 2 heads in n tosses is equal to the probability of n on 2 heads in m tosses for all m is equal to n minus 1 and n being an even number. So, thank you for watching, and this has been a Calero Academy production. Calero Academy will now start taking questions and suggestions for videos in its comment section. If you have an idea, just put it in the comment section and we'll see if we can make a video for it. Thank you for watching and goodbye. Stay tuned for more Calero Academy.